Good afternoon, physics students. My name is Mr. Williams, and welcome to the online lesson plan. Now, the purpose of this is that I'm going to outline our new project regarding physics and this cool website called Thinglink, where we're going to create interactive images that display all of our equations and can physically describe a situation happening in the real world. Now, the point of the online lesson in the flipped classroom is that so you get to see this instruction at home, and that when you come into class tomorrow, you get to use me as a resource for all of your questions, no matter what it is: physics, the website, the technology, the rubric. Anything you want to ask, you get to ask me tomorrow in class. Now, however, if you don't watch this at night, that is okay. You are still going to be able to complete the assignment. You'll just have to watch the introduction video in class, which means you'll lose out on some opportunities to ask me questions. However, this is all available outside of class as well, so long as you have accessibility to the internet. If you don't have access to the internet at home, you may use your off periods and the school computers in the library in order to finish this assignment. So let's jump right into it. We've been talking about physics for the past 2 weeks, and particularly kinematic equations of motion that deal with velocity, distance, acceleration, and time. Now, what does this all mean? We do physics, and we look at physics, and we study physics, not for the purpose of seeing numbers manipulated, not for the purpose of understanding vocabulary words. We learn and study physics to look at the world around us and how it all interacts with each other so that we gain another lens to view the world through. So let's do that. In this interactive video, what we're going to do is we're going to make an interactive image on a website called Thinglink. So let's check it out. What you need to do is type Thinglink into your computer, and you are going to click on the website. Oops, I happen to already be logged in, but what we're going to do is I'll log out and I'll show you what this looks like. All you have to do is you're going to click on this big button in the center that says Get Started. You're going to type in your email, your password. Go ahead and use your school email, make a password, create an account. You don't need to do anything else than that. Once that comes up, I'm going to just go ahead and log back in real quick. You will be sent to a site that looks like this and will be able to create. But before that, let's talk about what we're creating, right? So we look at physical situations in the world and we try to describe them with physics. Now, physics can get so much more in depth than what we're working on right now. Kinematic equations of motions are really good for building a foundational understanding for how things move. And so what we want to do is we want to take that and continue to apply that to situations. Now, they're not going to be completely accurate, and that is okay, because technically every situation is different. If two things are colliding, you're really going to be looking at elastic motion, which is significantly more complicated. However, the physical motion that we have right now can actually describe situations pretty accurately. So for me, I'm going to choose something with sports. And what we need to do is find a picture that represents a real life situation where two objects are moving, or two objects are in the picture, one of which has to be moving. There has to be some kind of motion to analyze with our kinematic equations. So let's take a look at it. For me personally, I think of sports. Now, this can be ice skating, football, basketball, soccer, golf, tennis, hockey, swimming, bike riding, what have you. Or you can go a route with two cars crashing, or a wrecking ball hitting a building, or a deer running away from a mountain lion, or somebody falling down the stairs. Good heavens. You pick the situation. However, try to pick only one point of contact between the two objects, or a single object moving, or two objects moving, just to keep the simplicity up. And if you have questions about what picture to choose, you can ask me in class and I will help you with it. And I'll tell you if the situation is too complex for you to describe or not. However, the example that I'm going to use is football. I grew up playing football and I love it. And I think it's a great example of showing kinematic motion. Now, I'm a Green Bay Packers fan, which is ironic because CSU also happens to represent their colors. Awesome. So let's type this in. Green Bay Packers big hit. Now I want to see a tackle from somebody because I think that those two motions would be great to describe that. Look at that picture right there. That is phenomenal. So what we are going to do is I found a picture that I like and I'm going to save it to my computer in a drive that I know I can access, because what you're going to have to do is re-upload this image into Thinglink. Now don't copy and paste this image because it won't work the right way. So you're going to save it, right? We're going to save image as, and I happen to have it as Clay Matthews tackle. So we'll just click on it and we're going to hit save. Yes, I would like to replace it. But we're not done, right? We want to model good digital citizenship. And so what that means is that we give credit to all the sources that we take information from. This source happens to be CBS Sports. So we're going to visit their website. And when citing an image, all we have to do is put the website link in the image with it. So we're going to copy. We are going to copy and paste this into a Word document, just so that we don't lose it and we continue to give everybody credit that deserves it. So I'm going to go ahead and open this up. Boom, a Word document. So let's go ahead and go back. Let's take a look at Thinglink. So what are we going to do? We're going to create. We're going to go up here to create, and we're going to upload an image. So what happens there, and then you're going to find the image that you found, which for me is going to be that Clay Matthews tackle. Boom. We're going to upload that sucker. And ready to go, my interactive image. Now what does this mean for us? We get to click and create tags where we can add a link, we can edit text, and more specifically, more importantly, we can describe the situation. So let's go ahead and take a look at the situation. What do we know about it? Well, we don't know too much. I am looking at Clay Matthews first in this situation because he is the one in motion. When Clay Matthews comes into the backfield, and we have to think abstractly about this, and that is okay. That is okay. We're going to look abstractly about it. We know that in a sack, which is what's happening, Clay Matthews runs from the backfield and hits Andrew Luck, right? So he is going to be the one in motion making contact with Andrew Luck, who is not. So let's analyze him first. But in order to do that, we need to know some stuff about him, particularly what he is as a human being. So let's see, we'll do Clay Matthews Combine Profile. So this is an NFL Combine site. And what this does is it gives me information about how Clay Matthews plays as a player and his physical characteristics. Now, what's really cool about this is that this is going to help us analyze the problem, and you're going to have to do this on your own too. There's going to be outside research that is necessary in order to make this make sense. We are taking a real life situation and trying to apply as much knowledge as we can to it. So let's see what that looks like. We have all this information, 4.6 second 40-yard dash, awesome. What that tells us is we can figure out his speed because we have a distance and a time. We also see his height and his weight, and that weight's going to be super important. So once we have all these facts down, you want to gather all your information. Let's start thinking about physics. Now, we look at the situation. Yes, I love my drawings as well. Clay Matthews is in the green helmet, and Andrew Luck's going to be in the blue. Now, Clay Matthews is rushing him in the backfield and is making that contact. So he's moving. Which kinematic equation can we use for that? We have all of these over here. These are the kinematic equations we've been working with in the past week. Scroll down just a little bit. That'll be over 2. V average is over 2. So these kinematic equations are what we have to work with in order to understand what the hit will actually connect with. What I am looking for in this situation is you to describe the physical characteristics of everything going on in the image. Now, if we go back to the image, what this looks like for us is Clay Matthews hitting Andrew Luck. Now there is a weight force involved with both of them because they're going to weigh different amounts. But there is also a kinematic force applied with Clay Matthews' acceleration and his mass because we know the second law, F equals ma. So that's what we're going to be looking at. So we're going to go ahead and pop into these notes over here. So I grabbed some of these statistics. Clay Matthews is 240 pounds, 6'3", and his 40-yard dash was 4.67 seconds. Oh my goodness, that is insane. That is a big man running really, really fast. But this information is not complete, is it? Now I look back and I say, awesome, I got all this information, but where did it come from? Online citizenship, or digital citizenship, tells us that we need to make sure that we source and cite everybody whose information that we use. So I'm going to go back into the website and go ahead and grab this URL, copy it, and paste it back into that Word document with our other ones so that we can keep track. Awesome. We want to continue to make sure we have our sources. So, like I said earlier, we're going to start analyzing this. I said that Clay Matthews ran a 40-yard dash in 4.67 seconds. That means he went 40 yards, which a yard is 3 feet, meaning that he went 120 feet in 4.67 seconds. So to find out his average speed in feet per second, we're going to divide the 120 feet by the time it took him to finish that. And we come out with 25.7 feet per second. Yeah. So let's come over here. What does that mean for us? What does that mean? We got his speed. We have his speed when he hits Andrew Luck. We also have his speed when he started because he's going to start from rest, right? The play is not going to start until the ball is snapped and everybody goes into motion. So you know that your initial velocity is also going to be 0. So which of these equations do we know? And what do we need? We know, again, that force is mass times acceleration. And the hit, the impact that Clay Matthews is going to make is going to be that force. And so we need to find his acceleration reaching Andrew Luck and the mass in order to make this happen. So let's solve for the acceleration first. Which of our kinematic equations can we use if we know the final velocity, the initial velocity, and the distance with which he covered? I'll give you a hint. It is this guy. Oops. It is this guy right here. We're going to take final velocity squared is equal to initial velocity squared plus 2 times the acceleration times the distance. Now, let's go ahead and scroll on back down and see how this works. So we know that we have this final velocity and all these different variables. So let's take our equation right here. Final velocity squared is equal to initial velocity squared plus 2 times the acceleration times the distance. Well, what does that distance look like? We shouldn't know, right? Oh, but we can. D, the distance from the outside linebacker to the quarterback in shotgun, which is where this play is actually taking place. And we take liberties. We're going to take liberties as scientists and assume certain characteristics. I am assuming that this play was taken in shotgun, which means that there is a direct distance that correlates with. You get to make these assumptions so long as you tell me what they are and explain why you made them. If you can tell me why you made this assumption and it's valid, then you have every right to make it, and I will never count you off for it. We as scientists have to think outside the box and use the information that we have to describe situations. So we're going to take that and run with it. I know from my own experience playing football that a quarterback in shotgun is 7 feet behind the line. I also know that a 5-step drop is an additional 5 to 6 feet considering I played quarterback. Now this is information that I took from my own head, but you might have to look somewhere else. This would be another place that you would have to cite your information if you took it from an online source. However, I know this from personal experience, so I don't need to, and I can take that liberty so long as I describe and explain it later. There's also the outside linebacker positioning of 3-4 defense, which is approximately 10 feet from the defensive line in the start of the ball. So our total distance is going to be the 7 feet of shotgun, the 5-foot drop, and the 10 feet that Clay Matthews has to run to reach the line, totaling at 22 feet. So we have our variables. We have our final velocity that we solved for at 25.7 feet per second, our initial velocity, because he's starting from rest, is 0, and our total distance between the line, the drop back, and the shotgun formation of 22 feet. So let's plug it into the equation, see what we get. With plugging this in, 25.7 squared is equal to 0 squared plus 2 times a, the variable we're looking for, times 22 feet. Well, what this comes out to is 13.67 feet per second squared. That means for every foot he's traveling, he is in, oh my goodness, he is cruising. My man is cruising and he is coming for a bruising. He is giant. So that's going to sting. So technically, when we look at acceleration, this is what we know as the derivative of velocity, which is another iteration taken against time. So we take velocity and compare it to time again, the same way velocity is the comparison between distance and time. So what does that mean for us? Well, we have the acceleration for F equals ma, but do we have the mass? The answer is no, because weight and mass are not the same thing. We need to remember that. So when we look back at that, what is mass? Mass is actually a variable, and we look at it in F equals ma. So where does the weight translate? Weight is actually a force. Weight is a force, and it's determined by mass multiplied by the gravity pulling down you on Earth. Now, since our mass happens to be in pounds, we're working in English units, which means that gravity is 32.2 feet per second squared. And so in order to solve for Clay Matthews' mass, using the information we cited and got from the NFL Combine website, we are going to take his weight divided by gravity in English units, which again is 32.2 feet per second squared. And what that's going to give us is a unit in slugs. Now, generally, slugs is a very strange unit. However, you can think about it in the same way as grams. Gram is not a weight. It is a mass unit, the same way that slugs is a mass unit in comparison to pounds. So let's take that. We do our math. We have 240 pounds of force, which is Clay Matthews' body weight, yikes, divided by 32.2 feet per second squared. That means we have a mass of 7.45 slugs. So what does that mean? Well, hold on. Am I still recording?